Here's the question. This whole video hangs on. What is actually inside a black hole? Not the movie version, the real answer, according to the physics we can defend. It sounds like it should have a clean answer. Black holes are the most studied objects in modern astrophysics. We photographed their shadows. In 2019 and again in 2022, detected their collisions through gravitational waves over 100 times. And watched stars orbit the 4 million solar mass monster at our galaxy's center closely enough to earn the 2020 Nobel Prize. And yet, the interior remains the one place in the universe where our two best theories, general relativity and quantum mechanics, walk in together and start contradicting each other. So this video is structured as an honest descent, layer by layer, what we know of the edge, what the math says just inside, what probably happens deeper, and the exact point where knowledge ends and educated guessing begins. Our flag is transition, because the difference between measured, derived, and speculated is the whole point. First layer, the boundary itself, the event horizon, and the genuinely unsettling fact that you could cross one without noticing. The event horizon is the most misunderstood boundary in science because it isn't a surface, a wall, or a membrane. It's a line in space-time's bookkeeping. It marks the radius where escape velocity exceeds the speed of light. And since nothing outruns light, everything inside is causally cut off from us, permanently. Here's the part that rewires intuition for a supermassive black hole. Crossing it would feel like nothing. No jolt, no flash, no alarm. General relativity is explicit. Space-time at the horizon of a big black hole is locally smooth. The curvature there is gentle precisely because the hole is huge. Sagittarius A star's horizon spans about 24 million kilometers. The tidal difference across your body there is negligible. You'd float through the point of no return mid-sentence. Now the flip side, and this is measured physics, not speculation, a distant observer watching you never sees you cross. Light climbing out of deepening gravity stretches and slows. Your image redshifts, dims and freezes at the horizon like a photograph fading to black. Two incompatible experiences of the same event, both correct in their own frames, and relativity's first lesson about this place. Inside questions and outside questions have different answers. Just inside the horizon, the mathematics does something that sounds like poetry, but is literal equation level fact. The roles of time and space exchange. Outside, you move freely through space while time drags you forward whether you like it or not. Inside, radial direction, inward, toward the center, acquires the properties time used to have. Falling deeper stops being a choice about motion and becomes the future itself. You can no more turn around and fly outward than you can, out here, decide to move toward last Tuesday. This is why every escape fantasy fails. More thrust doesn't help. Because the exit isn't in a direction anymore. The exit is in the past. Physicists put it cleanly. Inside a black hole, the singularity isn't a place ahead of you. It's a moment in your future as unavoidable as tomorrow. And the size of the hole sets how much future you have. For a stellar mass black hole, the proper time from horizon to center is microseconds. For a giant like M87s, an infalling traveler could have hours of subjectively normal existence, thinking, observing, recording. Inside a region, the universe outside is written off as gone. All of this is still standard general relativity, solved and agreed. The trouble starts at the destination. Before the destination, the descent gets violent. And this layer is uncontroversial physics with the best name in science, spaghettification. Gravity weakens with distance, so as you fall feet first, your feet, being closer to the center, are pulled measurably harder than your head, and the difference grows without mercy. Near a stellar mass black hole, this tidal stretching exceeds what steel endures, let alone tissue, long before the horizon. You arrive as a stream of particles drawn into a filament. Spaghetti, as Stephen Hawking cheerfully described it. Around a supermassive hole, the same fate simply relocates deeper inside, gentle at the horizon, inevitable near the center. This isn't idle theory. We've watched the process from outside. Astronomers now routinely catch tidal disruption events. Stars that wander too close and get shredded into glowing streams, half swallowed, half flung outward at a fraction of light speed. A famous one, Assassin 14Li, in 2014, let researchers track the debris orbiting and feeding the hole for years. So the stretching is real, observed, catalogued. What we can't observe, even in principle, is a final address all that matter is heading toward. And here's where I have to start flagging speculation, because the map's next label is the singularity, and the singularity is probably a lie. The math tells when it breaks. The textbook says at the center lies the singularity, point of infinite density, where space-time curvature becomes infinite. Here's what working physicists actually believe, almost universally. Infinities in physics aren't discoveries, they're error messages. When an equation outputs infinity, it's usually the theory announcing it has been pushed past its jurisdiction. General relativity is a theory of smooth, continuous space-time. At the center of a black hole is being asked to describe conditions where quantum effects, which it completely ignores, must dominate. It's the wrong tool confessing. The honest statement is, at some scale near the center, probably around the Planck length, 10 to the minus 35 meters, relativity stops applying, and whatever really happens there belongs to a theory of quantum gravity that we don't yet possess. The candidates are serious but unproven. String theory replaces the point with vibrating structures, sometimes called a fuzzball. Loop quantum gravity suggests space itself is granular and may bounce, matter compressing to a finite maximum density and rebounding, possibly forming what some models call a Planck star. Every one of those sentences is speculation, mathematically motivated, experimentally untouched. The singularity, as popularly imagined, an actual infinite point, is the one thing almost no expert thinks is literally there. And now the deepest layer, the one that turned black hole interiors from an astrophysics niche into the central battleground of theoretical physics, the information paradox. Quantum mechanics has one non-negotiable rule: information is never destroyed. Burn a bookend, in principle, the ashes, smoke, and light still encode which book it was, scrambled but recoverable. Then, in 1974, Hawking showed black holes aren't eternal. They leak, radiating energy, Hawking radiation, and over unimaginable timescales. A stellar black hole takes 10 to the 67 years. They evaporate completely. Problem: his calculations said the radiation is featureless, random static carrying no trace of what fell in. Black hole evaporates, book gone, information deleted, quantum law broken. That contradiction has now driven 50 years of the field's best work. Hawking himself conceded a famous bet in 2004, accepting information probably escaped somehow. The modern near consensus, sharpened by the holographic principle, and the 2019, 2000 and 2002 wave of calculations involving so-called islands and replica wormholes, is that information does get out, subtly encoded in correlations within the radiation, and that the interior may be less separate from the exterior than it appears. Some formulations, like ER equals EPR, even conjecture the inside is stitched to the outside by microscopic wormhole-like entanglement. Label: brilliant, contested, unverified. Paradox is the strongest hint we have that space itself might be made of something deeper. So, the honest answer to what's inside a black hole, folded into one map with the confidence levels attached. The horizon, fully understood, locally unremarkable, crossable without sensation, that's established relativity. The interior flow, space and time swapping roles, the center becoming your future, still solid theory, universally accepted. The approach, tidal shredding, observed from outside in real stars, as certain as astronomy gets. The center, not an infinite point, that's a theory breaking, real answer awaiting quantum gravity. Best guesses involve fuzzballs, bounces, or granular space-time, all speculative. And the fate of what falls in, probably preserved and eventually re-emitted in scrambled form if the last 2 decades of theory are right, still being fought over in journals this year. Notice the shape of that answer: certainty at the edge, decaying smoothly into honest ignorance at the core, and physicists knowing precisely where each transition happens. That's what real knowledge looks like from inside, not a wall of facts, but a well-lit map with the dark regions clearly labeled. The dark regions are where the next revolution starts. Every day, this channel takes one more question apart layer by layer, and tomorrow's is the opposite direction: what happened in the first second of the universe and how much of it we can actually prove.